In this refrigeration lecture, we're going to be talking about refrigeration theory. Now, what we want you to do is understand the basics of why we need to remove BTUs, what we're doing with refrigeration, and how it affects the food and the foodstuffs that you may be dealing with as a course of refrigeration. So, to start off with, let's talk about a few terms that you really need to know. First, heat. It's a form of energy, okay? Cannot be created or nor destroyed, but it is always there as either heat moving from one location to another, heat moves from hotter to colder, and the refrigeration is another term. It's a process of removing heat from a space. We need to remove it from a space we don't want it and put it into a space where we really don't care if it exists or a space where we want it. That's the process of refrigeration. The British thermal unit, or the BTU, it's the conventional unit of measure of heat. A BTU is defined as the amount of heat required to raise or lower the temperature of 1 pound of water, 1 degree Fahrenheit. So again, how many BTUs does it take to raise and lower the temperature of 1 pound of water, 1 degree Fahrenheit? That's what a BTU is. Substances other than water require different amounts of BTUs, but everything with a BTU is based on 1 pound, 1 degree Fahrenheit. Thermodynamics, it's the law of thermodynamics state that heat will always move from warmer to cooler areas. So when you leave the door of your house open, if it's cooler outside, the heat wants to go out. If it's hot outside, the heat wants to come in. Pressure. Okay, we got to talk about pressure. Standard atmospheric pressure is 14.7 psia, pounds per square inch absolute. Okay, that's an important number you need to remember because everything we do with gauge pressure, with building pressures, is built on that standard atmospheric pressure of 14.7 psia. Refrigeration gauges are calibrated to read 0 psig, that's pounds per square inch gauge pressure, at standard atmospheric pressure. So at 14.7 psia, which is standard atmospheric pressure, gauges will read 0. If you move to a higher or lower pressure environment, you have to recalibrate your gauges. Vacuum, its pressure is below atmospheric pressure, okay? Most often vacuum is going to be read in inches of mercury or microns. The compound gauge, which is the low side gauge on your gauge set, is a gauge that can read above and below atmospheric pressure. This is usually the left side of your manifolds, okay, if you're using non-digital manifolds. At above atmospheric pressure, the gauges read in PSIG, which is pounds per square inch gauge, starts with 0. Below atmospheric pressure, the gauges will read in inches of mercury, or HG is the term for inches of mercury. Then we move on to some heat terms. Sensible heat is a change in temperature that you can measure with an ordinary thermometer. So when you say the room is warmer or the room is 72 degrees, that is sensible heat. Latent heat you cannot measure. Latent heat is the heat that causes a change in state. So in other words, when I take and melt 32 degree ice and it becomes 32 degree water, because there's a point at which it's just changed state, it moves from a solid to a liquid at the same temperature. That heat, the amount of BTUs that's required to make that change, is what causes a change in state. Now, brings us to the term change in state. It's a conversion of a substance from one form to another. It's not a temperature change. It's a molecular structure change. For example, water to ice, ice to water, water to steam, steam to water. Okay, we're not changing what the fact that water is made up of H2O, 2 hydrogen atoms and an oxygen atom. We're saying now that the bonding is different, okay? Water in ice format is a solid. Water in liquid format is a liquid. Water in steam format is a gas. So that is a change of state. It's a conversion of one form to another. Specific heat is the amount of BTUs it takes to raise the temperature of 1 pound of any substance 1 degree. Now, we have to think about that because BTU definition is the amount of heat it takes to raise the temperature of 1 pound of water 1 degree Fahrenheit. So the specific heat of water is 1. Specific heat of spinach, milk, or any other food substance, any other substance, is going to be slightly different from water. But water is your reference point. Water has a specific heat of 1. Ambient temperature, the temperature of air that's around an object or device. So, in other words, you're sitting in a room, the ambient temperature around you might be 72 degrees. The ambient temperature around the building outside might be 40 degrees or 90 degrees. The ambient temperature is very dependent on what the ambient temperature is with reference to. Is it a condenser that's outside? Is it a house? Is it a room within a house? Is it a refrigerator within a room within the house? All have a different ambient temperature because it's the temperature of the air that's around an object or a device. Enthalpy is the total amount of heat that's around a substance. Okay, so every substance has a different enthalpy. Okay, a ton, okay, it's a refrigeration rating that is calculated when BTUs are known. 1 ton equals 12,000 BTUs per hour. Okay, so if I have a ton of refrigeration, I can remove 12,000 BTUs per hour from the contents of that refrigerator. Compressor tonnage and horsepower tonnage are proportionally equal. 1 ton is 1 horsepower, which is 12,000 BTUs per hour. A temperature pressure chart is a cross-reference between temperatures, pressures, and boiling points of refrigerants. That chart can be electronic, could be on an iPad, iPhone, any other smartphone, could also be on paper. You look down one side of the chart, you find the temperature of a refrigerant. Then you look at the other side, you'll find the pressure points. Okay, the boiling point of the refrigerant is in the evaporator and the condenser. Then we have a couple different ways we have to talk about how heat is transferred. Okay, there's 3 methods of heat transfer that you need to be aware of. Convection is the heat transferred by fluid or air movement. For example, if I blow forced air heat through ductwork, I am moving heat through air. Or air conditioning, I'm cooling a space by convection when I'm using forced air conditioning. Conduction is a particle-to-particle transfer of heat. For example, if I put hot water coils in the floor, as with radiant heat, okay, and I heat the floor from the water, it's a particle-to-particle transfer of heat. There's no air involved. That's conduction. Radiation is the transfer of heat by rays. I sit in front of a window without a blind on a hot summer day. The sun is shining in the window and it's heating me up. That's radiation. Another example of radiation is look up over the registers at Home Depot. Okay, you have strips of heat strips up there. Okay, that might have a gas fire in them. They're shiny. That's radiation. You're heating the space directly in the rays, but you're not heating the full surrounding rays. So you feel warm as long as you stay in it. Back to refrigeration and away from the heating. High temperature refrigeration are like systems like flower display cases. They start at about 45 degrees and they end up to about 60 degrees. Most high temperature refrigeration, an example of it, is used in flower shops and candy storage. Okay, the box is not ever freezing. Okay, but because you really don't want to just give someone frozen flowers. So it cools it, but it's not freezing. Medium temperature starts at about 30 degrees and ends up at 45 degrees. It's used to store products such as dairy goods, beer, and wine. Many products won't freeze at 32 degrees, so you can actually lower their temperature to about 30 degrees. Okay, medium temperature refrigeration is what you would see with your refrigerator in your house. Okay, between 30 and 45 degrees. Low temperature systems start at 32 degrees and decrease from there. It's used in such things as frozen things like ice cream, frozen meats, meat storage. Now the key thing about low temperature refrigeration is we have to defrost the evaporator coil on occasion. Okay, the evaporator coil is going to start building up ice as it cools. just from the moisture in the air of opening and closing the door. So every so often, if we have to defrost the evaporator coil using a defrost cycle. We shut everything down, figure out a way to heat the evaporator coil, melt the ice off of it, then restart everything off after the water flows away. There's a temperature-pressure relationship for everything. Okay, the temperature at which a substance changes state, it's dependent on pressure. Lowering the pressure lowers the saturation or boiling point. Raising the pressure raises the boiling point. An example of this can be found in a pressure cooker. I raise the pressure and the boiling point goes way up for water. I lower the pressure enough of water and I can boil water at room temperature. That's the point of a vacuum pump. So there's some refrigeration calculations we have to worry about. Now, you really only need to know this when you're running across a problem condition. So, for example, something isn't cooling properly and you're not sure of the design of the refrigerator. So what you have to do is you have to find the total BTUs needed to cool a substance from one temperature to another. In other words, a truckload of lettuce coming in that's hot that needs to be cooled down to 40 degrees just to make it last. You have to find the net weight of the substance. You have to find the degree of temperature change, or we refer to it as the delta T. You have to find the specific heat of the substance from a table. And then you use the formula BTU per hour is weight times the delta T times the specific heat. So for an example, okay, we have 500 pounds of cranberry that are coming in on a truck. They have to be cooled to 35 degrees. So our delta T is 70 minus 35, which is 35. Okay, the BTU per hour formula says weight times delta T times specific heat. So we have 500 times 35 times 0.91, because the specific heat of cranberries from a table we have is 0.91. So our BTUs per hour that we have to remove to cool these cranberries in 1 hour is 15,925 BTUs per hour. Another example, and here we introduce a really neat chart. A grocery store takes in 400 pounds of cucumbers and needs to cool them from 93-degree truck to a long-term storage temperature of 45 degrees. We want to calculate the BTUs that need to be removed. So our delta T is 93 minus 45 is 48. The specific heat of cucumbers is 0.93. So we have 400 times 48 times 0.93 in specific heat. Now we don't have any latent heat because we're not doing a change of state. We're not going to take those to ice cucumbers or gaseous cucumbers. We're just going to take it to a cooler form of the solid cucumber. So we end up with a total BTUs of 17,856. Sort of makes sense. Now, we're going to go to our third example. We have 50 gallons of water, okay, going from 75 to 35. Specific heat of water is 1.0. Remember I said water is a reference substance. That's 1 pound of water, 1 degree Fahrenheit, 1 BTU. So that's an easy reference substance. So our delta T is 75 minus 35, so we have to cool it 40 degrees. 1 gallon of water is 8.345 pounds. That's a number you want to memorize. 1 gallon of water is 8.345 pounds. The weight, the total weight that we're dealing with is 8.345 times 50, because we have 50 gallons of water. So our total weight is 417.25 pounds. So we fill in our magic chart down below, 417.25 pounds times 40 times 1. So the total BTUs I need to remove is 16,690. Okay, so, and that can be done in an hour, or if I have a bigger refrigeration system, I could do that in half an hour. Just double the BTUs, and all of a sudden I am now cutting my time in half. The only substance with a specific heat of 1 is water. To find the total BTUs needed to cool a substance from one temperature to another with a change of state, you still have to find the net weight of the substance. Then you find the degree of the temperature change. Okay, you find the specific heat of the substance and you find the latent heat of the substance. Then you find the temperature at which it changes the state, and you calculate the number of BTUs prior to the change and after the change and for the state change. Then you add them all together. So let's do a calculation. A warehouse gets 100 pounds of celery. It's delivered at 70 degrees and it needs to be cooled to -10 for long-term storage. How many BTUs are needed? Okay, so what we are doing, we have calculated that celery freezes at 29.7 degrees. And you'll see that the chart evens out here. So we have a sensible heat change from 70 to 29.7. Then we do our freezing, which is latent heat, no change in sensible temperature. Then once we're frozen, we go down to from 29.7 to -10. So we have two sensible heat changes and a latent heat change. Let's see how it looks on paper. Okay, we have 70 to -29.7, which is 40.3. Then I can freeze the substance. There's latent heat in there. Then I go from 29.7 to -10, which is another 39.7 degrees. The latent heat, that's the amount of BTUs I have to remove to take solid cucumbers to ice cucumbers, is 135 BTUs. So when we fill out our chart, we know we have 100 pounds of cucumbers. We can fill that out all the way down. My delta T for the first sensible change is 40.3. My delta T for the second sensible change is 39.7. So I can take my 100 times 40.3 times 0.95, that's the specific heat of celery, and I come up with 3828.5. Then my latent heat change, which is my B, I have 100 pounds times 135, so that's 13,500. Then my specific heat changes for frozen celery. I have 100 times 39.7 times 0.48, and that gives me my 1905. Add it all together, and I come up with, it takes 19,234.1 BTUs to cool celery, 100 pounds of celery, from 70 degrees to -10. Now, the interesting part is all of the specific heat and latent BTUs do come from a table that you'll have to look it up for. Okay, because those are numbers you're not going to have memorized, but they make tables for just about every substance that you can have cooled food stuff and chemically. Okay, and again, back to this example, you'll note that some of the substances, for example, celery, has a different specific heat above and below their freezing point. That's something to be very aware of and careful of. So a blank table you would take like this blank table, you'd fill in your pounds, your delta T, that's your temperature change, above and below the freezing point if you're crossing a change of state, specific heat above and below freezing point. You do your latent BTUs and you do total BTUs. Add it up, that's how much refrigerant in an hour, how many BTUs it's going to take to cool that substance. So in this lesson we did talk about some terminology. We talked about the calculation of BTUs for substances, and we talked about a little bit of gauges, pressure.